Alright, so today we're going to talk about the notion of partitions and probability, and then go on to cover some basic rules of probability, and then finally talk about some basic distributions. Alright, so what are partitions? We say that an event A is partitioned into X events, A1 dot 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 all the way to AX, if A is equal to the union of A1, A2, and then all the way through AX, and A1, A2, and all the way to AX are mutually exclusive. So why don't we see what that looks like in our handy Venn diagram? So let's say that this little rectangle represents our event A, okay? And then our partitions are essentially mutually exclusive segments or like subspaces of A that add up, like in the end, to all of A. So if we partition this into 4 different partitions, we can have these separate events make up the partitions that make up A. And right now it may seem kind of redundant to define this terminology of like a partition, but later on, as we'll see, they play an important role in defining our rules and helping solve probability problems. So with that being said, let's get into some of the rules. So these are some of the basic rules of probability. So rules of probability. All right. So the first one is non-negative. This means that the probability of any event, let's just call it A, is always greater than or equal to 0. Second rule is our addition rule. And this states that if some event, A, is partitioned into, let's just call it A1, A2, all the way through AN, then probability of A is equal to probability of A1 plus probability of A2, and then sum that up with probability of AN. And we could get this simple expression because we're borrowing from the notion of a partition where all of these sub-events are mutually exclusive, and that's why we can just add up their probabilities, and that can give us the total probability of the event A happening. And our third rule is that totality is 1. And this essentially means that the probability of the entire outcome space, and so this is just the notion of an outcome space. So probability of any of the entire like outcome space, because the outcome space is just a set containing all the events, right? So this outcome space will contain every single set that is possible, and so the probability of that is always 1, right? Our if we are running a function through the entire outcome space, that it means that our total probability is always 1. So we can't have a probability over 1, or we can't have probability under 1. And so with these sort of 3 basic rules, we can sort of build up the rest of the rules that we have for probability, and that helps us sort of create the functions that will allow us to more easily deal with solving probability problems and reasoning with events and stuff. So let's get into one of those basic rules, and so that is the complement rule. And so essentially the complement rule is just the probability of not an event. So probability of not A is also, we can call, notation wise it can be like this, or like sometimes you'd also get like A bar, and all of these mean not A, and that is simply 1 minus the probability of A. And we can kind of think of this as, if this is our little outcome space, right, and this represents A, then everything outside of this, the shaded region, is not A, right? So if we find out the probability of A, and we know that the probability of the entire thing is just equal to 1, right? Because we said the probability of the outcome space is equal to 1, right? So essentially, this is like a simple area question where what's the area of this outside region, right? And that's just 1 minus the area of A, and that's just, we get that through the probability of A, and that's simply how we find the probability of not A, right? And this gives us like uh, another property, which is probability of A plus probability of A complement, so not A, is equal to 1. And again, we can, we just have to reason about how we previously did about the probability of the outcome space, etc., to sort of come to this conclusion. All right. Now we get into our second rule, which is the difference rule. And this essentially implies if A implies B, right? So for a previous video, that just means like A is a subset of B, since if like knowing A happened implies that B has happened, right? So that must mean probability of A is less than or equal to the probability of B, because A is always a subset of B, right? So if A implies B, then the probability of B and not A and A complement, and we can also represent this as just the probability of B, A complement. So whenever we see two events sort of like combined, concatenated, that just means an and, right? So it's just this, what we ignored it. So probability of B and not A. So what is that probability, right? So again, if we go back to our handy Venn diagram, we know that A implies B. So this circle is A, and then we have B is like some superset of A, right? We want to find the probability of B, so this, and not A. So it's just this area right here outside, and not including the stuff that's outside B but in the square. And quite simply, if we knew the probability of B, this is just the probability of B minus the probability of A, right? So it was really easy to reason about this through this diagram, right? And as we can see, like this diagram sort of helps us sort of come at how certain relationships between events are represented. Another way we could go for this is, we know that the probability the last rule that we'll go over is the rule of inclusion-exclusion. And this is a really important rule. So sometimes it's known as pi. It's the principle of inclusion-exclusion. And this means that, and this says that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of AB, right? So before, you might get confused with the addition rule that we defined in the beginning, where we said if we divide A into like smaller partitions, the union of all those partitions is simply the probability of A. So where is this term coming over here if we're still doing like a union? when we define the partitions, we also said all the partitions are mutually exclusive, right? We did not say anything about A and B and their relationships, and so that's why this subtraction term comes over here. More generally, the idea is whenever you have two events, right? So if we call this event A and you call this event B, right? There can be portions of that event A that can lie outside of B, right? There can be portions that lie in A and B, and that implies that A and B may not be mutually exclusive. They could, but they also may not, right? And so essentially, we know that this little this little portion over here, that is simply